forecasting with multiple Markov boundaries, and it's given by Kevin Chen. Now, he's Robert Chen. He's not one of the authors, but he's willing to take questions. So thank you so much.
Thanks. All right, so I'll be presenting a paper from Wei Ding's group at University of Massachusetts in Boston, and some other collaborators too, Kui Yu, Dawei Wang, Wei Ding, Pei Jian, David Small, Shafiqul Islam, and Xindong Wu. So the problem we're trying to solve is that tornadoes are very severe events and they cause a lot of damage, up to $3.6 billion in the US per year. And in order to help prevent in order to address this problem, I think it'd be useful to be able to detect tornadoes early. So there's several problems with current predictive modeling or predictive forecasting for tornadoes. Traditional methods that are used are employed currently by the National Weather Service. A lot of these are warning systems based upon simulations. And there's several big data-driven methods that are being proposed proposed recently. And the success of big data-induced process in studying the weather system is quite limited right now. So more about that. So for big data-driven methods, the main difficulty to model weather dynamics is in there's a couple problems. There's high dimensionality of data and very complex relationships in between different features that are related to weather patterns. So one way we can tackle this is to use dimension reduction to find a set of features that are most predictive for tornadoes. And then there's several drawbacks to current methods that interpretable precursors may be missed, and precursors identified could also be impractical. And without alternating options for domain scientists to select more reliable and physical interpretable variables. Here's an example. This slide shows an example of why having a single set of features, as many people might be doing now, is not necessarily optimal. So the first example is showing, trying to show that with low-level winds, high-level winds, and vertical motions at the same location, these may be considered equivalent precursors, which will lead to extreme precipitation. So this is, in a sense, weighting a bunch of features the same way. The second bullet is showing that current methods for feature selection might limit the choice of practical precursors. So although there's three precursors identified here, the low-level winds, high-level winds, and vertical motions, and then compared to high-level and low-level winds, vertical motion is usually a very noisy and unreliable precursor. So there should be a way to weight this one feature differently because of that. So the solution we propose is using multiple Markov boundaries to identify multiple sets of features, which would be precursors to tornadoes, and this would help domain experts choose practical and reliable set of precursors. So the main idea behind this method is to use multiple Markov boundaries to find several interpretable sets of precursors for tornadoes. And this would help domain experts to choose the most practical and reliable one after they're giving several options. So I'll talk a little bit more about Markov boundaries. So imagine a Bayesian network where P is a discrete joint probability distribution of a set of random nodes, which is specified by F, and is part of a direct acyclic graph. So the triplet F, G, and P, it would be a discrete Bayesian network if F, G, and P satisfies the Markov condition where every node is independent of any subset of its non-descendant nodes conditioned on its parents. And there's an important condition that needs to be satisfied called the faithful condition, which is basically saying that given this Bayesian network, the set G is faithful to P if and only if every independence present in P is entailed by G and the Markov condition. And following up on that, P is faithful if and only if there exists a direct acyclic graph G such that G is faithful to P. The figure in the bottom right shows this relation. And finally, the Markov boundary would be defined as the following. If a Bayesian network satisfies the faithful condition mentioned above for every node X, its Markov boundary is unique with the set of parents, children, and spouses of X. Above, I described the Markov boundaries. But now we want to incorporate multiple Markov boundaries for our data. So many real-world data distributions usually violate the faithful condition and thus may contain multiple Markov boundaries. So for example, in the example here, we're looking at the target node is T. So there could be two possible Markov boundaries here. So the set with X and Z, and also the set with Y and Z. So if there's only one single Markov boundary, say Y and Z, then we might be missing some information from the causative feature X, which would not be captured in the Markov boundary. So the main motivation is that multiple Markov boundaries would improve the discovery of underlying mechanisms and not miss some key causal variables. So this slide is showing an example of data from tornadoes, why this would be useful. So there's a couple of major challenges with the data that we have. So usually these data are large and in high dimensions. So a data set that has been widely used is a tornado data set with 13,000 observations that were collected over 35 years. And the total number of precursors for one instance could range up to 810,000 attributes. So existing algorithms of multiple Markov boundaries cannot deal with this large number of attributes, mainly due to computational costs. The other challenge is how to deal with distributed feature data. So there's a flood data set with more than 13 gigabytes total, and it's distributed into 8 variable sets. And each variable set has about 100,000 attributes. So basically, if we have multiple data sources, we would need an efficient way to deal with this. So what the authors proposed is an algorithm called MB-DEA. There's several steps to this. First, we find the core feature space, which represents the feature space of all possible Markov boundaries of a target attribute, and then confines mining Markov boundaries to core feature space instead of the entire space for the training data. This is to discover the feature space. We do that, and then we process one feature set at a time, and process one feature in each data set at one time sequentially. We load the whole data set in memory in advance to do this. Then we mine the multiple Markov boundaries from this core feature space that is obtained. So this slide is basically going over the main parts of the algorithm. So assuming T is a target attribute, then we would denote the Markov boundary as MB of T. Sorry, the notation is, I think it's because the PowerPoint was made on a Windows machine and this is a Mac. But the down arrows mean subscript and the up arrows mean superscript. So MB of T is a notation for Markov boundary of T. And so R refers to the set such that for all sets F sub I in the Markov boundary of T is a set of attributes correlated to F of I. And this means that R of F of I is a set of features that satisfies the condition such that for all F sub J in groups that are part of R of f of I, the mutual information between the subsets of each f are equal to 0. And then after doing this, we find the core feature space, which is defined as the following, which is the union of each of the separate feature sets. So this is a schematic talking about this. On the left side is showing the Markov boundary of T, and on the right side is showing the core feature space of T. So this slide describes how to find the solution for the set R of f sub I. So there's several main corollaries. Corollary 1 is saying that in a feature space S, a feature X is correlated to feature Y if the mutual information is 0. Corollary 2 is basically saying that if f sub I is correlated to T and set C, then the mutual information of two sets is equal to 0, then the mutual information of f sub I with T is greater than the mutual information of f sub J with T. And corollary 3 is saying that if Markov boundary 1 and Markov boundary 2, which is, I think, a subset of Markov boundary 1, then both are also Markov boundaries of C, then the mutual information. And if the mutual information is 0 for both of them, then the mutual information of either Fi or Fj are greater than the max of the mutual information of either one with C. So this is a schematic of the general process. So we basically have a bunch of feature sets and process all the features in each one sequentially. And we check during each iteration if the new feature belongs to the core feature space. And if so, we add to the core feature space. And we repeat this process until we've iterated through all of the original data sets. This is a summary of the algorithm. So with the core feature space, we use the MB-DEA algorithm in the following steps. So first is discovery of the core feature space. And after we discovered the core feature space, we used the TIE algorithm, which is an existing Markov boundary algorithm to mine Markov boundaries from the discovered core feature space. To evaluate how well MB-DEA works, we compared MB-DEA with TIE, and we used several data sets. So yeah, we compared MB-DEA with the single Markov boundary discovery algorithms on our tornado data. And these are the data sets that were used. So there's 8 tornado data sets where we tried this. So next, we'll show the results from real-world data. So we show the F ratio and the MB ratio for this. And the F ratio was defined by the authors as the ratio of number of features of the core feature space discovered by MB-DEA divided by the number of total features in the data set. So they range from about 0 to the highest is 0.16. And the MB ratio is the ratio of number of Markov boundaries discovered by MB-DEA compared to the number of Markov boundaries identified by TIE. So basically, this is showing that most of the Markov boundaries that our algorithm discovered can also be discovered with the baseline method. So basically, we used the features obtained with our algorithm and put them through a classification algorithm and tested prediction accuracy. So this chart is comparing the accuracy between our algorithm, which is in white, and the baseline TIE, which is in blue. So we're getting pretty similar classification accuracies in both methods. So we also looked at the running time of MB-DEA. And this is compared with the baseline method as well. So yeah, the times in seconds are shown in both columns. So some of them, the algorithm for TIE, the authors weren't able to run it. So it's crossed out. So basically, as you saw in the last slide, the MB-DEA algorithm achieves similar accuracies as TIE, but as this slide shows, we're able to achieve similar accuracies but take up less running time. So this graph is just showing the running time on each of the data sets. So the Dexter and Thrombin data sets took the most time to run out of all of these. Other evaluation metrics that were used with the features obtained are accuracy and F1 score. So this is a flowchart of the evaluation method. So if you look at the first two columns of this, so the first left half of the chart, we took the entire data set and downsampled the data at different ratios. And next, after that, we took each data sets and put it through the MB-DEA algorithm, and we found that the Markov boundary and the core feature space from the Markov boundary. So this table shows the results. As you can see, each line represents a different downsampling ratio, and as you go down the table, each line represents more undersampling, and the best average F1 score was highlighted, which was over here, was 0.31, and the best F1 score is highlighted here, 0.35. This is just a schematic graphical example of how we go from a single Markov boundary to a core feature space. So the graphic at the bottom of the slide shows the core feature space and the best features. And similarly, this is just another example. This slide is basically showing the comparison of using different criteria for picking the best feature sets. So at the top is using single Markov boundary, so the baseline method, and then we can pick new feature sets with the best using best prediction power or most reliable variables. So there's several conclusions we have from this. The MB-DEA algorithm was proposed. It's a scalable approach to find multiple interpretable precursors to tornadoes. And the main point is that if predictive features are found beforehand, then a domain expert can predict tornadoes and prevent them. So the authors would like to acknowledge several parties that helped to support them, including the PIMS Postdoctoral Fellowship Award, discovery grants from NS, ERC, and national grants from China. So that will conclude the presentation. Thank you. All right.
Thank you. Very interesting presentation. I'm curious about what was your prediction horizon and what in the end were the features which were selected in terms of physical features like humidity or.
In terms of the actual what the features were. I don't think they showed it. But you could probably email the authors.
How about the prediction horizon?
About the prediction horizon, like how much time?
Yeah.
Yeah, I'm not sure. Sorry. That's definitely an important thing to consider.
All right. Let's thank our speaker once again.